Hello, everyone, and welcome back to the final part, hopefully, of chapter six, in where we'll be talking a lot about enzymes. So, in the other parts, we spoke a lot about, the free energy, which is basically the total amount of energy that can be used to do work. That's, free energy. And then we spoke a lot about changes of free energy and specifically what happens with the free energy when, you have reactants that, there's some chemical reaction occurring and you get products. So we measure more the changes of the free energy there from the reagents to the products. And we know that if products have a higher free energy, than the reagents, that is a endogernic reaction, meaning that we need to actually give energy to that. It does not happen spontaneous. But the opposite, where the reactants have more free energy than the products, that's an exergonic reaction, and that can happen spontaneously. But things don't happen just spontaneously because if that would be true, our basically car would be running constantly because the burning of the petrol or fuel is actually a very exergonic reaction, but that doesn't happen constantly. It doesn't happen just spontaneously like that. It can, but we need to just add it a small activation energy. That's the minimum amount of energy, this amount of energy, this extra amount of energy. That's the right word. One sec, this is going a bit nuts. Mm-mm-mm. There you go. So the activation energy is that extra energy required to start an exergonic reaction. And the activation energy really dictates a lot the rate. So if you have a huge activation energy, then the rate of the chemical reaction, so how fast reactants are being produced into products, will go very slowly because you need a lot of activation energy. However, if you lower the activation energy, the rate actually increases. So, how can you decrease the activation energy? Well, it's by using catalysts. And an example of a catalyst are enzymes. So enzymes are literally, they can be, most of them are proteins, but some can be RNA, which we'll talk about later. But these are basically compounds that act as biological catalysts. So what they do is they actually love to bind to substrates and they like to break, or help break bonds. They will bind to substrates, so basically in this case your reactants, they'll bind to them, and what they do is they will basically help lower the activation energy by making the chemical bonds more fragile. So they will bend them, make them a bit more uncomfortable, and then basically it kind of helps then for the to lower the amount of energy needed to break those first couple of bonds. And those are basically enzymes. So these guys, as we said, they lower the activation energy because they're catalysts. So what does that then mean? That means you really actually increase the rate of reactions. And let's take an example here. You guys remember this equation? Carbon dioxide plus water gives you carbonic acid, which is the biggest buffer. This is what's happening basically in our blood constantly, right? This carbonic acid really helps us, keep our the pH of our blood, neutral. So it acts as a buffer because this can be both acidic, but also can be then, gone into a more basic solution as well. So this process over here, this without any enzyme, if you go and do this in the lab and you just add carbon dioxide and water, this will actually happen. This will give you 200 molecules of carbonic acid per hour without any enzyme. This is very slow, especially where our body is actually exposed to a lot of things that can change the pH of our blood. So this would not really help us that much. We need to make this much, much faster. How would you do this? Is by actually adding an enzyme. Because when you add an enzyme, suddenly you basically go from 600,000 molecules formed per second, not per hour, per second. So you've increased the amount by almost a million. Imagine that's that you've increased that rate by times 1 million. That's incredible, and that's what I mean with catalysts and enzymes. What they do, they reduce this activation energy, which then really make the reactions much much faster. So all they do is really help the rate. So not nothing to do with basically giving energy or anything like that. It just reduces the activation energy, which then makes the rate much faster. So let's take a look at an example about an enzyme. And most of these enzymes are proteins, these very nice globular proteins. So what these guys have, they have this really nice growth, which is this opening over here. That's the growth. And we call that the active site. It's active site because basically this is the site where the substrates, so our reagents, will bind. And this binding is very actually specific. So meaning that this enzyme will only bind to a specific substrate. It won't just bind to any substrate around. Enzymes are very specific. They will only actually bind to specific substrates. So keep that in mind. So once they actually bind, this is quite nice and locked. However, what happens is that this enzyme now creates this enzyme substrate complex. So this is the enzyme with the substrate that creates this complex. When it binds, the enzymes actually will move and kind of, move their hands and create a better fit. And this is called an induced fit, where basically the whole enzyme is inducing a better fit. So as you can see here, this binds here, and then these arms over here, they're just pushing down and closing on the substrate. And what this does is that when it creates this really nice induced fit, it really helps to kind of make these bonds very unstable in the substrate, which really does help then to break the substrate later on to reduce because you're actually putting so much stress on the chemical bonds. You need less energy then to break them. So that's the whole concept of an enzyme actually. So this comes actually out of an experiment because people were thinking a lot about, okay, are proteins, very rigid, meaning that they do not move? Because in this case here, this whole protein is actually moving. It's kind of, its arms around these here are kind of going in this direction to create this induced fit. So you start thinking, is like, are protein structures flexible or are they rigid, meaning that they do not move? Prediction is antibody antigen binding can involve a change in protein structure. So meaning that you have antibodies which bind to antigens. Antigens are these proteins that the antibodies bind to. This could be, for example, influenza, this could be a bacteria or whatever. So you do a test. You get a crystal structure. So a crystal structure is just an image that tells you more the structure of a protein. You take a picture before the antigen and so before and after the antigen is bounding. And then you see just the structure. Has it changed? Because if it changes, then it means it's flexible. If it has not changed, it's rigid. So the result is after binding, antibody folds around the antigen, forming a pocket. So as you can see here, this is much open. Now this is more closed. So it's able to actually move. Conclusion, in this case, binding involves an induced fit kind of change in conformation. So that when these proteins, like antibodies, are binding to another protein, they actually love to move and make this kind of let's put it this way, this binding more of an induced fit to kind of change the conformation to make it more nicer, this binding. That's what it means. So there's further experiments. Remember, again, not just one experiment can really prove a proper hypothesis or prediction. So here, the further experiment is like, why is this experiment easier to do with an antibody than an enzyme? So here we've done it with a protein like an antibody, but an antibody is not an enzyme. So why has this not been done in an enzyme? We know about this proteins, but this is also include enzymes. So you need the next experiment is to be done with an enzyme. Can this be done with an enzyme? Quite hard actually, because enzymes the crystal structure to determine the crystal structure is quite not that easy. You can do it with certain techniques, but it's not as easy as an antibody. Okay, so now let's take a look about more the active site. The active site is this site in where the enzyme has, where the substrate is binding there. So your reactants are binding there. They bind there and you create an enzyme substrate complex, like I was talking about. So this is basically here. So this is your free enzyme. You have two states of an enzyme. Free enzyme, meaning the enzyme has no substrate, and you have a enzyme substrate complex. And that's when the substrate is binding to the active site, which has the growth. And basically, the substrate precisely fits in the active site, and that's what makes enzyme specific. That substrates have to precisely fit in the active site. It's not that it's just random. It just it in any kind of way the substrate can bind to the enzyme. No, no, no. It has to be precise. And then there are certain, basically, once it binds, the enzyme will move its arm and kind of make this fit even nicer. So this is induced fit. And when you actually have this nice induced fit, you're applying a lot of stress on the bond of this substrate. So that's why you're reducing the activation energy, because activation energy is an energy needed to just to break the first chemical bonds. Well, if you have the enzyme that is binding to your substrate right now and it's kind of bending this bond, well, it's going to become much easier to break it. And think about it as a stick. Imagine you have a stick in your hand. Breaking a stick when it's basically not stressed is much harder if I bend the stick now and then I can really basically break it easier. And I'll give you here an example. So let's imagine here basically you have glucose and fructose all bound together. So this is sucrose, which is glucose and fructose. And they're basically, having this nice bond. The enzyme basically is going to bind to the enzyme. So as you can see, it fits really nicely. And there's an induced fit. As you see, these arms over here, they're open. But when this binds really nicely, as you can see, like quite precisely, these arms basically are now kind of collapsing in and making this induced fit. It's kind of making this binding even better. And you can see now, look at the bond here, which is straight, and now look at the bond here. So much pressure is being added there. So to break this is much easier than break that. So then you add water, because how to break this is by hydrolysis. Remember, this is from chapter 3 in macromolecules. How to break this is hydrolysis. How to create, how to make monomers stick together is through dehydration. How to break them is through hydrolysis. So water comes in, and this kind of really helps the breaking of this bond. So you break it, glucose and fructose then leave, and then you have the enzyme back again. And this enzyme can be reused quite a lot. So when you have a chemical reaction happening, you don't need a lot of the enzyme. You just need a bit of it because they keep recycling. They can basically they don't. It's not that they just basically break a bond and they're useless and now you need to throw them away. No, they're still active. So that's why when in chemical reactions you don't need a lot of enzymes. This is the cool thing. So enzymes can be found in multiple ways. They can be actually just in the cytoplasm, just freely walking around, or they can actually be attached to cell membranes. For example, we have the cell membrane, but they can also be in organelles. And specifically, you will see that a lot in mitochondria. In mitochondria, you have a lot of enzymes that are stuck in the cell membrane of the organelle in there. And that's just to keep the location of certain chemical reactions, specific in certain areas. So you want to keep certain reactions in the mitochondria, then you stick that enzyme in the mitochondria in this cell membrane. And they can be basically just one unit of a protein, but they could be also this multi-enzyme complexes. I'll give you an example is this pyruvate dehydrogenase, which is a enzyme that you see actually in bacteria. This enzyme is a literally a multi-enzyme complex that is made of three different enzymes, and there's 60 of them. So it's three different enzymes, and there's 60 copies of them that come together and create this big complex. And this is quite of an advantage. It actually has three advantages. The product can be delivered easily to the next enzyme, unwanted side reactions are prevented, and all reactions can be controlled as a unit. Meaning when you have this multiple enzyme complex, which in this case you have three enzymes, together, what happens is that when you, for example, in a chemical reaction, you might have multiple steps. For example, you have three steps. So each step might need a different enzyme. So here you have them all together. So when the first step is done, you can directly transfer the product to the second enzyme, and the same thing, the second enzyme can then deliver its product to the third one straight away. So you're not losing time, because imagine if these three enzymes were um, found in different places. Well, the substrate has to go to enzyme one, then the reaction is done. Then it needs to travel and then go into basically enzyme number two, and then it does it, and then it has to travel again to enzyme number three. Well, here you actually stop all of that because they're all together, and it's much faster. Two, you have unwanted side reactions prevented. So meaning that, for example, in step number one, the first substrate, goes to enzyme number one, and you create a product. Well, this product, before it goes to step number two, can be taken up by another enzyme and can give you something else. Well, you prevent that by actually having them all together. And all reactions can be controlled as a unit because they're all together. You can control them much easier because they're one unit. Compared to if they were separately, then you have to control them all three differently. Well, here they're all together. You can control them as one, which actually can be quite great. So you can stop this whole reactions, this sequential amount of reactions, so this one, two, and three reactions, just by tackling one complex, not three different complexes. So as we said, enzymes, most of them are proteins. However, this is basically before 1980s. We always used to think that enzymes are all proteins. But then in 1981, we discovered that that was not true. We started to see actually that enzymes are can be non-proteins. An example is RNA. They found out that RNA can be actually, catalyze certain reactions, and they can catalyze them by their own or in actually complex with another molecule. So there's two kinds. There's the intramolecular catalysis. These are RNAs that are basically quite nicely folded, and they can catalyze reactions by itself. So the RNA by itself can do the reaction. Or they actually act on another molecule, so they are attached to another molecule, and together they actually will catalyze a reaction. And that's called intermolecular catalysis. So intra is inside, meaning that the RNA inside itself can do the catalysis. RNA is basically outer, so more basically with the molecule. So one thing about enzymes is that how can you further increase it? So we know that enzymes can increase the rate of reactions. But how can we further increase this enzyme catalysis? How can we make this enzyme catalysis even faster? Well, there's two ways. There's four ways, sorry. One is substrate. So the amount is if you have much more substrate, the enzyme catalysis is much faster. Also, if you increase the amount of enzyme, you increase the amount of actually the rate. Because in this case, you have much more enzymes that are doing a lot of this catalysis happening. But also, you can play around with the temperature and pH. And we'll be talking about what optimum temperature is and optimum pH is. So let's just talk here just quickly about temperature. Temperature, one thing that we know that it loves to do, temperature likes to move bonds. When you increase temperature, bonds start to shake, they start to move. And that's how, while in a chemical reaction, when you increase heat, you're decreasing you can decrease actually the activation energy because you're making the bonds unstable. And if you lower the reactions, you make the chemical bonds very rigid. They don't move. So sometimes you want to find the perfect temperature. You want to find the temperature in where bonds are moving, but not too much and not too little. Because think about the enzyme. The enzyme, what it needs to move, remember, to do this induced fit model, the enzyme has to move. So if you put very low temperatures, well, the enzyme is not going to be able to do that. So if the enzyme is not able to move to do this induced model, it's not going to do pressure on the substrate. So it's not going to catalyze. So it needs to find the perfect temperature. So not too cold that it's not able to move, but not too hot that the enzyme is shaking so much that it's not actually properly, able to produce stress. It keeps shaking. So that's called the optimum temperature, meaning as you can see here, this is like one enzyme, and this is the rate of the reaction. So for example, here at 40 degrees or at 40 degrees, this enzyme is working at the highest rate. So this is called the optimum temperature. It's finding the best temperature at which the enzyme works best. So here you have one enzyme and you have another one here that works at 70. Different enzymes have different optimum temperatures. It all depends. So human enzymes, they usually like to work around 40 degrees. For example, prokaryotes, certain bacteria that actually live in very hot temperatures, like kind of hot springs, they work at 70 degrees and more, which makes sense because the environment is quite hot. So they need to adapt to that. Another one is basically pH. Because what pH does, if you increase pH, you can drive amino acids to become basic or acidic. So sometimes you need the enzyme to be acidic or basic depending on what they're doing. For example, pepsin. Pepsin is found in the stomach. So you want this to be very acidic. So you want to actually make the amino acids positively charged. And if they're positively charged, they can actually break down a lot of things in the acidic environment. So that's why it has an optimum pH. So a perfect pH is where the basically it's amino acids can become positively charged to do the work. And same thing goes to trypsin. Sometimes even trypsin, which basically works in basic conditions or more basic conditions, not fully because this is more on the 7, 6. This is still acidic, but it's more basic than of course here. So this they increase the pH because you don't want it to work. You don't want too much positive ions. You want them to shift more to the negative. So how you do that is by adjusting the pH. And of course, so basically, enzymes they can work better at certain temperatures and certain pHs. So you need to find the optimum temperature and the optimum pH, meaning that the perfect pH for it to work at its finest, at its best capacity, and the best temperature. So now let's talk about inhibitors. So these are a class of substances that they bind to enzymes and will decrease its activity. So it will basically inhibit, as the name say, inhibit the catalysis of enzymes of the substrate. So it doesn't let the enzyme catalyze substrates anymore. And there are two different types. There's competitive inhibitors and there's non-competitive inhibitors. And I want to say this here, guys, starting from inhibitors, study from the slides. Do not study from the book, only in the case of inhibitors, because the book is a bit outdated. Inhibitors really have changed because we used to have a certain perception of them, and now we realize that this is not true, that things have changed. And literally, the things that have changed, we've actually put them with a nice, we've struck them to show you what changed. So now let's talk about competitive inhibitors and non-competitive inhibitors. So to really understand competitive and non-competitive inhibitors, you really need to actually go back and really memorize that enzymes have two states. They have a free enzyme, meaning the enzyme doesn't have any substrate. And then you have the enzyme substrate complex, meaning the enzyme is bound to the substrate. So hence, enzymes, two different phases or two states. Free enzyme and enzyme substrate complex. Keep that in mind. And this is very important to know because competitive inhibitors will only bind to free enzyme. They do not bind to an enzyme that has a substrate. Okay? So we used to think that basically competitive inhibitors they compete with substrates for the active site. That's not true. It competes with the substrate to the free enzyme. So the free enzyme either will bind to the competitive inhibitor or to the substrate, but not both. That's what competitive inhibitors are. Non-competitive inhibitors is basically they bind to both the free enzyme, but also the enzyme substrate complex. So they're able to do that. But competitive inhibitors, they don't. Competitive inhibitors, they only bind to free enzyme, while non-competitive inhibitors will bind to both states, to free and to basically enzyme substrate complexes. So we'll go into more details about this. So here you go. So let's start with competitive inhibitor. So as we saw, competitive inhibitor only binds to the free enzyme. And we used to always think that this only happens that the competitive inhibitor only binds to the active site. So remember this site where the substrate binds. That's what we used to think. Then we later realized that no, that's not true. It's often the competitive inhibitor can bind to the active site, but sometimes it also can bind to other sites that will impede the free enzyme to bind to the substrate. And I'll give you your examples. So the first classical example is that. So I is the inhibitor and S is the substrate. That they have basically bind to the same site, so basically the active site. So that's why when the inhibitor is bound here, the substrate cannot bind. And it makes sense because if the substrate is bound, this inhibitor cannot bind to the enzyme anymore. So this is why competitive inhibitors only bind to free enzyme, because when the substrate is there, the inhibitor cannot bind. So this is the classical model. B is that the inhibitor basically does not bind to the active site, but it sterically hinders the S. So meaning here, for example, it will basically bind to its other site than the active site, which is here. However, its protein kind of structure will stop the substrate from going in there. It just theoretically hinders it. It just kind of forms some sort of kind of block from it to not to actually bind. That's one. C, if you see here, S and I binding sites are overlapping. So you clearly see, for example, that the inhibitor doesn't bind to the active sites, which are here, basically here and here in the triangle form. It doesn't bind to them, but it binds to other. So basically, the inhibitor binds to one site that kind of competes with the substrate because it doesn't let, for example, the substrate bind anymore to the other active sites. So that's one way. D, S, and I have a common binding pocket. So, for example, here this is the active site. They basically, the inhibitor can bind to two pockets, and basically one of them is the active site and can push the S away. E is that the inhibitor binding can result in a conformational change that prevents Si from binding. So the I, when inhibitor actually binds, as you can see, it changes the active site. So this becomes much, much more smaller, and this conformational change doesn't allow the substrate anymore to bind. So substrate has to leave. So these are basically all examples of competitive inhibition, and they all have something one in common, which is very key for competitive inhibition, is that the inhibitor can only bind to free enzyme, and once it's bound to free enzyme, it does not allow the enzyme to bind to the substrate, and vice versa. If the substrate is bound to the free enzyme, so creating this enzyme substrate complex, the inhibitor cannot bind anymore. So always remember that. So now let's go to non-competitive inhibitor. Non-competitive inhibitor binds equally, and this is super important, equally to both free enzyme and the enzyme substrate complex. So the non-competitive inhibitor, as the name says, is non-competitive. That means it doesn't care if the enzyme is bound or it's not. It will bind anyway because it doesn't compete with the substrate. And this can be, for example, in this kind of form. So the inhibitor binds now basically here, and the substrate can still basically bind normally. However, so I'm going to show you an example of here, for example, when the substrate only binds. As you can see here, if you look at the C, this is basically the enzyme. When the S binds, the C basically now moves around. This is again the induced fit model. This happens basically because this inhibitor is not bound. So the substrate is binding to the enzyme now does this induced model. However, what can happen is basically the inhibitor can bind to this complex, so basically the enzyme substrate complex, and can push away this induced model. So it makes the protein more rigid. So when you push this away, this is not able to stress the bonds anymore, the chemical bonds here. So it's not doing its catalysis anymore. So you're preventing it. And vice versa, basically, here is that in a free enzyme, the inhibitor can still bind. And will basically, if the S still goes in there, the substrate binds, this will not do the induced fit anymore. So this non-competitive inhibitor is kind of changing the enzyme in a certain way. It's not changing really the active site. Sorry about this again. My computer's going crazy. Give me one sec. So the inhibitor here is actually not really affecting a lot the active site, but it's what it's doing is actually inhibiting more this induced fit model, and that's how it can prevent the enzyme from doing its job. And or basically you can also sterically hinder. This is very similar to the non-competitive, but the difference here is that the inhibitor can bind freely or without. So basically, as you can see here, you have two states. This is the free enzyme. So the free enzyme, the inhibitor binds perfectly, or this is basically the enzyme substrate complex. So you can see the inhibitor can still bind. And when this binds, it really prevents this induced fit model again to happen. So that's what basically occurs. This is how it can inhibit. So now we have mixed inhibitors. So mixed inhibitors are very similar to non-competitive. However, basically you have unequal affinities to both free enzyme and enzyme substrate complex. So you have inhibitors that they prefer more the free enzyme, or some that prefer a bit more the enzyme substrate complex. These are mixed inhibitors. Can they have mixed um, properties? As remember, non-competitive have equal. They bind equally to free enzyme or enzyme substrate. Mixed, no, they have a preference to free enzyme, for example. So they have a mixture of both competitive and non-competitive. And here you have basically an example in where you have the inhibitor that basically the inhibitor here, for example, here as you can see, is that the inhibitor can bind here, but not so well. As you can see, this is quite poor, basically quite small. Only when the substrate that is bound there, it can bind. It can actually go down because now it opens this up. So that's why this inhibitor can still go in there, but it prefers if the substrate is bound there. So this is an example of uncompetitive inhibitor. So now let's talk about allosteric regulator. So allosteric regulators are literally substances or compounds that bind to the enzyme in a different and that bind to the enzyme in a different place, meaning that they do not bind to the active site. They bind to other or in addition to the active site, meaning that they don't. So most of the enzymes basically bind to proteins to the active site. Well, allosteric regulators are ones that basically bind to other sites or the active site and another site. That's what allosteric regulator is. And this can be both activators or inhibitors. And these allosteric regulators, because they don't bind to the active site, you start thinking, okay, but if they don't bind to the active site, can they stop the enzyme from doing its work? Well, they do a conformational change in the enzyme that prevents them from doing the work. And this conformational change can actually affect the enzyme substrate active site complex, which we've spoken about. It can actually affect the stabilization of the transition states, but it can also reduce the ability to lower the activation energy of catalysis, which we'll talk about. So these are allosteric inhibition. So let's talk, in a more competitive allosteric inhibitor. So competitive meaning that the inhibitor only can bind to the enzyme when it's free. So when it basically binds the inhibitor, the enzyme's active site basically changes. So remember the because it's allosteric, it doesn't bind to the active site. It has to bind to another site. It can bind to the active site, but as long as it also binds to somewhere else. So in this case here, it's binding to another place that's changing the active site conformation, and is preventing the S from not basically touching it anymore. That it's not able. This subject cannot anymore bind anymore down here. It just cannot because the inhibitor has caused a conformational change. So now let's look more in a non-competitive allosteric inhibitor, which we spoke about. So non-competitive meaning that the inhibitor doesn't really care if the enzyme is free or not. So in this case, where it's actually free, the inhibitor is going to bind and it's going to basically create a conformational change, not in the active site, but around it. So when the substrate binds, this induced fit model will not allow it. So this basically C part will not be able to attack the S, so will not basically come close to the S and will not stress the substrate anymore. So it's not going to put stress on the bond, on the chemical bonds. So as you see here also, basically the inhibitor doesn't really care, just because it's non-competitive. It doesn't really care that the substrate is bound. It will still bind and will push away this induced fit model. So this is allosteric because it binds somewhere else than the active site. So it's bounding, it binds there, and basically, does not allow the induced fit model to happen. So you're not pushing the bonds to break. So those are all basically different types of inhibitors. You have the mix, you have basically, of course, we spoke about competitive and non-competitive and the mix. And we also spoke about allosterics. So basically, these are inhibitors that bind in a different position than the active site. So now let's talk about more enzymes. Inside the enzymes, in especially the active sites, you can actually have additional chemical components that we call them cofactors. And these guys really help the enzyme do its job. And I'll give you here an example of metallic ion zinc. So in the active site, you can have a lot of zinc ions in there. And what they do, these zinc ions, because they're literally very positive ions, they can really damage or help damaging chemical bonds. So these are the active little functional groups inside the the enzyme that can do the damage. And these are known as cofactors. These are basically, are together with the protein, the enzyme that are breaking it. And you can also have any cofactor that is non-protein, so it's an organic molecule like vitamin B6. So you can actually have a whole organic molecule like vitamin B6 in the enzyme that is really helping to break down chemical bonds. And this is these then are basically called coenzyme. So it's basically the co is the additional part of the enzyme. So now the final thing that I'm going to touch about is metabolism. So metabolism is basically, as we know, is the process and where our body you basically uses to create energy, not to create energy, basically to build molecules for energy or to break them down. And you can basically divide them into two ways: anabolic reactions or anabolism, or catabolic reactions or catabolism. So you have a lot of reactions that help build up molecules for energy. So you basically expend energy to build molecules, and this is called anabolic reactions, anabolism. And catabolic reactions or catabolism is literally the opposite. It's harvesting energy by breaking down molecules. It's when you break down molecules to harvest energy. Here, you're using energy to build molecules. So that's the difference between anabolism and catabolism. And one thing that if you guys remember that I was talking about, there's sometimes where you have multiple chemical reactions that are happening in a sequence. Well, this is called the biochemical pathway, in where you have multiple reactions happening right after the other. And I'll give you an example here. So imagine you start here with an initial substrate, which goes to enzyme number one, gets catalyzed, does the first reaction, and then you have this intermediate substrate A, which needs to then go to enzyme two to give you B, and then again to B to give you C, and then to enzyme four to give you the end product. And this is coupled, so they're literally one after the other, and this is called the biochemical pathway. And you will learn this a lot. And for example, when we have glucose, when you want to break down glucose to give us energy, a lot of things have to happen. There's a lot of different types of reactions that are done successively after each other to break it down. And that's called the biochemical pathway, and where you have multiple reactions happening, one after the other, to get to the end product. And sometimes you need to control that. Sometimes, for example, let's imagine here that you get too much end product and you want to stop basically this reaction because you don't want to, because we don't need much more of this, and you don't want to basically, run out of your initial substrate. So you need to control it. And how one way to control it is by using a feedback inhibition, in where the end product by itself can be an inhibitor. So let's imagine, for example, here where you have the initial substrate, you're creating it from enzyme 1 to 2 to 3, and you have your end product. This end product can actually be an allosteric inhibitor, so it can be either competitive or mixed, and they can basically combine here. And what it does, it really prevents, and basically it kind of closes the active site. Kind of does this kind of conformational change, and this will stop the whole reaction. So this is one way of how a biochemical reaction can control itself, by how when you have too much product, the product by itself is an inhibitor of the first enzyme, so you stop the whole pathway to happen. In this case over here, enzyme, when you have basically there's the end product that does not bind, this will keep going and going and going until something stops it, but it's not going to be the end product. So one way of actually doing so is having the end product be an allosteric inhibitor. So this is the end of chapter 6. If there's any questions, please guys feel free to contact me. Thank you.